I'd like to welcome you all to Computer Mathematics, and the star of computer mathematics is the place value system. And so to illustrate the place value system, we will start off with the very first topic, which is converting binary numerals into decimal numerals. So binary numerals is sometimes called base 2. And the reason why binary numerals are called base 2 is because there are actually two digits. Namely, the two digits are 0 and 1. So that's binary. Two digits, 0 and 1. Decimal, by contrast, has 10 digits. And that's called base 10. And the 10 digits in the decimal system of numeration are 0, 1, 2, all the way up to 9. So 0 counts as a digit, just like in binary, base 2. 0 is a digit. It's a recognized digit. It's a very important digit. In decimal, base 10, 0 is also a digit, a very important digit. And so if we count up the number of digits in decimal, base 10, we actually get 10 digits because the 0 counts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, a little mathematical piece of notation that you will see in college courses. We have a comma followed by 3 dots. The 3 dots collectively is called an ellipsis. Now don't confuse the 3 dots, which is the ellipsis, with the mathematical concept of the ellipse. The ellipse and the ellipsis are different things which should not be confused. But I go off topic. But in college level mathematics, you will see this. You'll see if the person writing a sequence in mathematics feels that the pattern is self-evident, then that person will use an ellipsis to save time and space. LOL. That stands for laughing out loud. Okay, so let's get to some examples to illustrate converting. Oh, so the other thing we need to understand is what's called the place value system. And I'm just going to call the place value system PVS for short, the place value system. So I'm going to start off with something you already know, but my experience in teaching is that it's a really good thing to start the students off with what they already know, even if it's boring and they already know it, and then relate it to something which they might have thought they knew, but didn't really know it. But when they relate it to what they have already known and they see how simple the connection is, they'll be like, oh, it's really that simple. Oh, now I understand. So that's what I'm going to do now. So I want to start off with the decimal system of numeration, which you already know. And let's consider the number 437. 437 in decimal. Now, you've already been to high school, I'm assuming, if you're taking a college level math class. So you would read this as 437. This 4 is not actually a 4. This 4 is a 4 in the hundreds place. So this 4 actually means 4 times 100. That's what it really means. It doesn't mean 4. It means 4 times 100. This 3 really means 3 times 10 because it's in the tens place. And this 7 doesn't really mean 7. Does it? Well, actually it does. Because this 7 is really 7 times 1, which is 7. So this 7 actually does mean 7, but this 3 doesn't mean 3. This 3 means 3 times 10, which is 30. And this 4 means 4 times 100, which is 400. Now, where does the 1, the 10, and the 100 come from? So I want to write this down. 1, 10, 100. I'm even going to put 1,000. So where do these numbers come from? Well, I'll tell you. 10 to the 0 is 1. 10 to the 0th power is 1. 10 to the first power is 10. 10 to the second power is 100. And 10 to the third power is 1,000. So the decimal place value system, which you knew, but you may not have known it in such clear detail, is based on powers of 10. Now you do have to know that any non-zero number to the 0th power is 1. This is an essential thing, and I could prove it to you if you shoot me a comment and you want me to prove to you why 10 to the 0 is 1. I'm happy to do so, but you'd have to actually shoot me a comment that would show me that you actually care. Okay, so these powers of 10 you're probably very familiar with. But let's look at the binary system of numeration, because the binary system of numeration, since there are 2 digits, is not based on powers of 10, but rather it's based on powers of 2. 2 to the 0th power, 2 to the first power, 2 to the second power, 2 to the third power. Let's go to 2 to the 4th power. So, of course, any non-zero number to the 0th power is always 1. You know that, of course. If you don't know that, you better know it. 2 to the first power is 2. 2 to the second is 4. We have 8, and then 16. And this can go on, 2 to the 5th power is 32. So this is the pattern. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. It's about as far as I can go in my head. but that is the integer powers of 2. So the binary place value system is now based on these powers, 1, 2, 4, 8, 16, 32, 64. So let's do an actual example. So let me write example. And I'm just going to walk over to make sure this really is in the frame, because I moved my clipboard a tiny bit. We're doing a high-tech video here. Yeah, okay, it's in the frame, and my thing is counting. This is good. All right, so let's do an example. So let's convert 10110 to decimal. Now I'm going to put a little subscript 2 under this number. Right? This little subscript tells us that this is a binary number. Right? So the decimal number 2 does not actually exist in binary, but as a subscript. Now you should know that a subscript is below the number. As a subscript, all this notational element is telling the reader is that this is a binary number. Okay, so your first step, step 1, your very first step would be to put the place value system above each digit. So remember we had 1, 2, 4, 8, 16, right? These are the powers of 2. 1, 2, 4, 8, 16, 32. Just like in the decimal system of numeration, we have 1, 10, 100, 1,000. So this is the way it is in binary. So what I'm going to do is I'm going to just put those place values. Now that's what they're actually called. They're actually called place values, and that's why this thing is called the place value system. Okay, so that's your first step. So step 1 is just place values. All right, we got that. All right, so step 2, what we're going to do is it's called expand. So we're going to take 1 times 16. Now this is where we got the 1 times 16. Plus 0 times 8. And this is where we got the 0 times 8. Plus 1 times 4. 1 times 2. And 0 times 1. So I want you to see the pattern in what we call the expansion. So notice the binary digits are 1, 0, 1, 1, 0. And the coefficients here, 1, 0, 1, 1, 0, right there. And I just stuck in the place values as multipliers, 1, 2, 4, 8, 16. And if it was a bigger binary number, 1, 2, 4, 8, 16, 32, 64, 128, 256, do it that way. Now, the next thing is take out your calculator or do it in your head. In a college math class, you're typically encouraged to use calculators. You're encouraged to use whatever technology of the day exists. Because in college, one of the missions, it's not the only mission, but one of the missions is to prepare you for the real world. And so in the real world, you'll never go to a company and they say, oh, by the way, you're not allowed to use calculators. Wouldn't that be absolutely ridiculous? You better know how to use a calculator. You better know how to use a computer. So if there are teachers out there who are watching this video for their students, and you say to your students, I don't want you using a calculator, I'd like to say, in my humble opinion, you might be doing your students a little bit of a disservice. Unless you're teaching elementary school, that's a whole different thing, because they have to learn arithmetic. But if you're teaching high school, you got to start preparing your students to enter into the real world. So not only should they be able to use calculators, but also they should be able to use computers. All right, so this is 16. This is a big fat 0. This is 4. This is 2. And this is a big fat 0, and I forgot the plus sign, but I'm putting it in. So 16 plus 4 is 20. And 20 plus 2 is 22. So the answer is equal to 22 base 10. So this little subscript here tells you that it is base 10.